Right, welcome to Chapter 7. We are getting into a pretty short chapter on some systems of equations and matrices. First part of this will definitely be review for you guys as we look at systems. The matrices should be the new part for you. So a quick couple reminders here. If we were looking at a system of equations, remember a system of equations just means you have more than one equation. And the purpose for these is because you have more than one variable, right? So if I have two variables, then I need two equations in order to solve it. If I had three variables, I would need three equations to solve it. So as I look at this, quick trip down memory lane on solving a system by substitution. So if this is our system of equations, in order to use substitution, the first thing we got to do is isolate one letter. So if you look at that x right there, that would be the easiest letter to isolate because it doesn't have any numbers attached to it. All you would have to do is subtract that 3y over to the other side, and you would get x by itself. You could then sub that information into x in the other equation. So if you look down here, that's what they did. So they isolated the x in the first equation, plugged it into the second equation for x right there. That was the statement that we got plugged in for it. And then now you can go through and solve this equation for y. You get your answer for y. And as you guys know, all I have to do with this answer is plug it back into either equation in order to get my value for x. So quick support on this graphically. Remember, we can solve a system of equations by graphing it. In order to do that, you would want to get y by itself in order to solve this graphically. So let me just back up real quick so you can see both equations. So on the very first equation, if I were to get y by itself, I would have to subtract the x and then divide everything by 3. So that's what I'm going to do on this. So on top I would have 8 minus x, and then I'm dividing everything by 3. So there's the first equation. On the second one, we would have to subtract 3x and then divide everything by -2. So let's do that. So I got my 13 minus 3x, and then I'm dividing everything by -2. So here's our graph. And you'll see it looks just like the ones that you're going to see on the page over here. Because of course you could do this like in Desmos, any graphing system. Can easily graph these guys. The key on this, of course, is making sure that we know how to identify that point of intersection, especially if it's not an integer, and you can't do it just by looking at it. We need to go under this calc function right there. So I'm going to hit second and then calc, and we are looking for this guy, the point of intersection. Right, guys, we can see the point of intersection is the only point that is on both graphs, right? It's the only point that satisfies both equations, which is why it's our solution. So we're going to take that intersect. All I have to do is hit enter, enter, enter. And there's our point of intersection at 5, 1. So supporting that answer that we got algebraically. And so all of that's going to look like review to you guys. So let me jump down to this one over here. So we're going to jump down to the second example, solving a nonlinear system by substitution. So obviously the one that we just did, they were both lines when you graph them, right? Anytime you have an equation where your exponent on x is a 1, you have a linear equation, right? X to the first is a linear equation. And so that's what we just solved, was a linear system. But what if we had a nonlinear system? So on this one, it's talking about the dimensions of a rectangular room. It gives us the perimeter and the area. So notice the significance of that is we're given two different pieces of information that we can use to set up two different equations. So I can solve one equation, or set up one equation for perimeter. I can set up another equation for area. And so that's what's going to happen on this one. So of course the perimeter is going to be 2 widths plus 2 lengths gives you your perimeter. Length times width would give us the area. So there's the two equations that we are solving. Guys, again, the goal is still the same. I need to pick one of those equations and somewhere isolate one of my letters in order to do that. And there's a few different ways you could do this one, but here's the path they went down. They said, let's just look at this first one. one of the first things that's very easy to do on this equation is just divide everything by 2. And you get this new equation that says x plus y equals 30. And that's a whole lot simpler to deal with, because then I can very simply subtract x over and get y by itself. And so that's what they did to that one. So they took that 30 minus x and plugged it in for y on the second equation. And that's our substitution move. It looks like this. And again, now we have a basic equation to solve. Notice on this one it's not linear, it's quadratic. Right? So we have a quadratic equation to solve on this one. So we're back to our quadratic tools like factoring or quadratic formula. Obviously they chose quadratic formula on this one because it was not factorable. So they're solving this with good old quadratic formula. And again, guys, we could still solve this graphically. Right? I could go back to these two equations, get y by itself, and graph them, and find those points of intersection just like we did on the first one. All right, so you can do the same thing with your graphing tool to find that point of intersection. Here's one thing I want to make sure we point out though. If you were doing this by hand, as you solve with the quadratic formula, notice you will get 2 different x's. Right? We're solving a quadratic, I'm going to get 2 solutions. So I would have to take turns plug in this one in order to get the y value that goes with him. And then I would have to plug this one in order to get the y value that goes with him. When you write those answers, you do want to write them as ordered pairs because you want to know which x went with which y value. Right? And so it's important to write those guys as ordered pairs so that we can separate which ones go together. And then just one more quick mention on this, guys. Do understand, if you're dealing with like a word problem, do understand your parameters on your domain, on what you're allowed to have or not allowed to have. If we're talking about a rectangle, length and width and areas and things like that, do understand that none of those values could be negative. So you'll notice on this one they did sort of establish a domain and range that would be acceptable. Right, so we had to have some positive numbers in there in order to get valid solutions. So if you're solving a problem like this, it's like a word problem, understand what's going on in the word problem because it might eliminate some of your possible solutions. Right, if one of those points of intersection would have been a negative, I would not have kept it as part of my answer. So just always keep that in mind. It's something to consider as you're doing word problems. Let's try one of those together. So we're going to practice one here. So here is our system right here. Now, if you can think back to your Algebra 2 days, you spent a little time with conic sections, which would be like a circle, parabola, hyperbola, and ellipse. And when you did those, this was one of those conics that you're seeing right here. Anytime you have x squared minus y squared, we're dealing with a hyperbola. Hyperbolas are the ones that do something like this, kind of like the Hurley symbol, right? So anyway, let's go ahead and solve this guy. So what we want to do is we want to isolate the easiest letter to isolate, which would be that y value right there in the linear equation. So of course we would just subtract the 2x over to the other side. So in that first equation, we would subtract over the 2x. And get that idea right there. And now we're going to take that expression, plug it in for y into this equation. So let's say x squared minus, and here's our y squared, equals 3 times y. Alright, so there's our substitution move. The rest is simplify and solve for x. So let's go through that real quick. So I'm going to say x squared minus, and if I were to expand this guy, in other words, if I did negative 2x plus 5 times negative 2x plus 5, and you FOIL or distribute, we would get 4x squared. Let's see, that would be minus 20x plus 25. Guys, notice I kept the parentheses here because that negative is going to distribute. That's important that we don't forget about that. Let's go to the right side of the equation and distribute the 3. So we got a negative 6x plus 15 over there. So now I'm going to distribute my negative as well as combine like terms. So I'm looking at an x squared minus 4x squared, which is negative 3x squared, plus 20x minus 25. You guys, here's the point where we're going to recognize, of course, I'm solving a quadratic, which means I want to get everything onto one side and make it equal 0. So I'm going to add the 6x. Actually, I'm going to bring those guys over to here because I want to make my leading term positive. So I'm going to go up to the top here. Let's add the 3x to the right, 3x squared. Let's subtract the 20x. So now I'm going to have negative 26x. And add this 25 to make this 40. All right, so here's where we're at. The first thing I would look for before I continue is, could I shrink this down? Is everything divisible by anything in common? That doesn't look like we have that. I can't divide everything by 3, so I would just have to throw this into my quadratic formula and go from there. Let's do that real quick. So what is 26 squared? So b squared minus 4 times a times c all over 2a. So there's our setup. Let me figure out the square root here. Actually, I'll just put it all in. So let me do my fraction mode. So let's do 26 plus . So there's one of our solutions. And of course you could write that as a decimal if you want. Let me just keep it as an exact value for the moment. So there's one of our solutions for x. Of course I would change this to a minus in order to get my other one. Oops. So I'm just going to change that plus to a minus to get my other solution. Right. So those are my two x's. I just have to take turns plugging those back in for x in order to get my y value. And of course that would be the easiest location to sub them back in. So I would just take turns plugging those back in and getting my y values to go with it. Alright, let's talk about the elimination method. So another popular method for solving a system. Guys, typically we only use the elimination method if we're dealing with common exponents. So these are both linear systems, which is why I can do this. If one was linear and one was quadratic or whatever else it might be, probably could not use elimination if they don't have the same exponents on them. But elimination goes something like this. I would like to be able to add these two equations together and eliminate one of my letters. So in this case, that wouldn't happen if I did it right now, because if I added these together, I get 5x. Here I would get negative 3y. Obviously, that doesn't eliminate anything. So we say, well, let's multiply these equations by something that are going to set them up for elimination. So what they chose to do here in the book was they said, let's multiply the top equation by 5, the bottom equation by 8. That way, he will be negative 40, he will be positive 40. So then when I add these two equations together, the y values will cancel. And so that's exactly what they did here. My one side note on this is, if you multiply this top equation by 5 and the bottom one by 8, make sure that you multiply everything in the equation by that number. Right? Because oftentimes people maybe forget to multiply it over here, and they might leave this as 24 or whatever, and so that will obviously snowball through the rest of your problem. So They multiplied those two equations, and now they said, well, let's just add everything straight down. So that became 34x. That became 0y, so that became eliminated. Over here you got the 136. Now you have this really simple equation to solve where you divide both sides by 34. And that gives you your answer for x. And then just like the other ones, you would plug that back into either equation to get a value for y. And then we just always best to write that as an ordered pair. Helps us identify which letter was which. So these are all just reminders. I know you guys have done this plenty of times, so I'm trying to just give you some reminders and work our way through. Quick reminder on our two special cases. The no solution case or the infinitely many solution case. Guys, the no solution case is the one that looks like this, right? Where you have parallel lines, so they never intersect. Therefore, you'll never have a point of intersection. There's no point in common to both equations. And so you don't have any solutions for that. That's our no solution case. Best way to recognize that is if you were to look at the equations where you got y by itself. This is the best way to view it. Because as I look at these equations, I can see that they have the same slope. But they start in two different places. So they have two different y-intercepts, but they're going to run the same direction, which means they'll never meet. Right? So same slope, parallel lines, no solution. If you were solving this algebraically, let's just say you went through the elimination method, and you said, well, hey, let's multiply this top equation by 2 so that I can set up my x's for elimination. So it looks like this. But look what happens when I add everything straight down. The x and the y get eliminated, and I'm left with a false statement. 0 equals 28 is obviously false. Therefore, I would recognize by a false statement that this is no solution. The infinitely many solution case is where, well, let me just talk about the graph. They're basically the same equation, right? It's like putting one line on top of another line. So if they have the same slope and the same y-intercept, that means they're going to start in the same spot and run the same direction. So you would just be writing one line on top of the other line. So in that case, they intersect everywhere. So that's why you say it's an infinitely many solution case, because they intersect in infinite locations. If you were doing that algebraically, the infinitely many case is the one where both letters get eliminated, but it's a true statement, like 0 equals 0. So let's just say that was 18, or sorry, negative 18. Then this would become 0, and then you would have a true statement. So then you say, oh, hey, that's my letters got eliminated, but it's a true statement, therefore it's many solutions. So I know you guys have seen all that before, but I wanted to remind you of what those things look like, because it's just may have been a while. Let's just peek at one last example, and I got to show you this word problem, and then we'll be good to go. So stick with me here for just a couple more minutes. So real quick, let's identify this. Real easy by saying, let's just multiply the top equation by 3. So if I did that, I would have, actually I'm going to use negative 3. Let me just identify that. So I'm going to multiply the top equation by negative 3. So it becomes negative 3x plus 9y equals negative 12. So as I add everything straight down, my letters both get eliminated. 12 and negative 12 is 0. So here's that case where we're saying, hey, all my letters got eliminated, but the statement I'm left with is true. 0 equals 0. Therefore, these are the same line. So even if I graphed them, they would intersect everywhere. So this is our infinitely many solution case. For that guy. All right, almost there, last page. Let me show you this stuff. $500 in savings account. I got a job where I'm making 15 bucks an hour. Not so bad. Your friend has 455 bucks in savings account and earns $17 an hour. So if you're both working the same amount of hours, how long until your friend has more money than you? Obviously, guys, even though I'm starting with more money, 500 bucks, I'm not making as much. So in time, my friend would overtake me and have more than me. So let's just set up a couple equations from this, and we'll take a look at this as how to interpret our answer here. So I have my 15 bucks an hour with my 500 bucks in savings. So my total, I'm just going to say my total is 500 plus 15 bucks per hour. So I'm going to let X represent the hours that I work. So my friend's total income is 455. With 17 bucks an hour. And so there's our two equations. You could pick your favorite method on how you want to solve this. You could use graphing. Just think of this as y, and you could graph it. Substitution would be pretty easy. You got methods here, multiple methods. So I'm going to substitute. So if t equals this, then this can be subbed in for t on that second equation. So it becomes 500 plus 15x looks like this. I'm going to subtract the 15x and subtract 455 and get that right there. Divide by 2 and we got 22.5 hours. There we go. Squeeze it in. So here's what you got to be careful on with this, and this is kind of the point I wanted to get to. How long until your friend has more money than you? Guys, understand that at 22.5 hours, you are equal, right? This is like, if I were to graph this, that would be my point of intersection. So at 22.5 hours is where we have the same amount of money. So X would have to be greater than 22.5 in order for my friend to have more money. So anything over 22.5 would really answer that question. The other thing you got to be careful on is, what question are they asking? Are they asking about X, or are they asking about T, or my Y value? Right? So T represented the total income. So they could have just as easily said, at that point, how much money will you both have? Or at 22.5 hours, how much money will each of you have, right? We're in some kind of a question to where I might have to plug this back in order to figure out what that total is at that point in time. So just be careful on the question that they are asking and make sure you answer it appropriately. I'll point to one example in your book and we'll close out the lesson here. So let me open up to page 516. So here's what example 8 looks like. So this one is now talking about, and this is a pretty popular question for this level, so this is definitely one you want to pay attention to. They're talking about the price and production of a product, right? So they're talking about these tennis shoes. When they talk about the equilibrium point for this system of equations, so here are the two different functions that we are looking at. One is the demand curve, right? That's like from the buyer's point of view. So this is a function that represents the demand for the shoe and the buyers for what they would want to purchase. The supply curve represents the maker of the shoe, right? The company, the manufacturer producing these shoe. This is like how they produce the shoe. So if you look at these guys, they're telling us right here that the price is P. That's the price of the shoe. And X represents the number of shoes in millions, right? In millions. So these are the two statements they're coming up with, and what they're looking at is what they're calling the equilibrium point. The equilibrium point is where demand meets supply, right? Where they are equal to each other. In other words, I am producing the exact same amount of shoes that the public is purchasing, which would be like ideal, right, for the company. Because if you don't produce enough, then you're going to say, well, I could have sold more, right? And you're not making as much money as you could have. If you produce too much and people aren't buying them, right, now you have overstock, and now you're losing money that way because you spent too much money making shoes that people aren't buying. So ideally, they want to figure out where do those two things come together. So they're just solving this like any other system, right? You could easily use substitution and set this or plug that in for P here, and that's what they did. So they figured out that at 5 million shoes, then supply will meet demand. So if we produce 5 million, people will buy 5 million, and those two things will go together. At which price will that happen? So if I were to take my 5, plug it back in for X, that tells me at $135 is when this will happen. So if all these functions and numbers were accurate, the company would say, okay, then we're going to sell our shoes for $135. We're going to produce 5 million of them. And in theory, that's when they would sell all of their shoes at the right price. Right? So again, this is very simple, just solving systems of equations, but the idea is understanding how to interpret what these things are talking about. So they can ask you multiple questions. They can say how many shoes would need to be manufactured in order to reach this equilibrium point, or they could say at which price, or they could ask you for both. So again, really important that you just know how to interpret the question that's being asked of you. But that is it for lesson 1.